Okay, so in section 8.4, we're going to talk about hypothesis testing of a single variance. So up to this point, we've talked about two of the main characteristics have been means and also proportions. But we could also do tests for another one of the main characteristics, which is variation. So the standard deviation, or typically we phrase it in terms of a variance. So here are just some facts about this. A couple of things to know: that it's a chi-square distribution is used, so different than the Z or T distribution. And it's actually non-normal, so it is skewed slightly off to the right. The larger your sample size, though, the closer it starts looking to a normal distribution. The population, if we're looking at the population distribution, the mean is the degrees of freedom here. And the standard deviation is the square root of 2 times the degrees of freedom. Okay, and so also when we graph it, our mean will typically be slightly off to the right of the peak. So here being our mean, and then right here being our peak. So usually it's going to be off to the side from there. And so for this test of single variance, this is how we get our test statistics, so the chi-squared. N is the total number of data, S squared is sample variance, and sigma squared is the population variance there. So chi-squared is equal to N minus 1 times S squared, that quantity divided by sigma squared. And so let's actually look at an example of one here. So math instructors are not only interested in how their students do on exams on average, but how the exam scores vary. So too many instructors, the variance or standard deviation may be more important than the average. So sometimes we want to look at the spread of our data rather than the average to see how everyone's doing. So suppose a math instructor believes that the standard deviation for his final exam is 5 points. One of the best students thinks otherwise. The student claims that the standard deviation is more than 5 points. So if the student were to conduct a hypothesis test, what would be the null, alternative, and the claim here? So similarly, we have our null and alternative. And we're going to use sigma here because we're talking about the claims that the standard deviation is more than 5 points. And so technically, that would be our claim there, that sigma is greater than 5. And that's the claim. And what we're going to do, though, here, what we're going to end up doing is we're going to change this up a little bit. This specific textbook, we're going to write everything in terms of the variance. So even though it's talking standard deviation, we're doing a test for the variance. So we're going to write sigma squared as the variance. But that means we have to write 5 squared as well. So our claim here ends up being sigma squared is greater than 5 squared. And then the null always gets the equal, as usual. So this would be a setup of our null, our alternative, and the claim. So let's get into a full example. So with individual lines, it is with individual lines at its various windows, a post office finds that the standard deviation for normally distributed wait times for customers on Friday afternoons is 7.2 minutes. The post office experiments with a single main waiting line and finds that for the random sample of 25 customers, the waiting time for customers have a standard deviation of 3.5 minutes. With a significance level of 5%, tests a claim that a single line causes lower variation among waiting times. So shorter wait times for customers. Okay, so we're trying to test this that having that single line is going to be more consistent. So sometimes you go to the post office and you might be, is it going to be 5 minutes? Is it going to take 30 minutes? So we would like something to end up being consistent for us. So this is a case where the variation might be more important because, we want to know if it's going to take long or short, right? That's kind of what we're more concerned about. So let's go ahead and go through this, the null and alternative here. And we're going to go ahead and write it as sigma squared, so the variance. And the claim here is test a claim that a single line causes lower variation. So that's going to be a less than. So we're going to say less than 7.2, but again, we want it to be the variation there. Okay, so it's going to be 7.2 squared. So for the variance. That makes that our claim, and by default, the null is going to get is sigma squared is equal to 7.2 squared. All right, second step, data and stats. So our sample size was 25. Our sample standard deviation was 3.5. Our degrees of freedom was 1 less than the sample size, 24. And so our distribution we could write as chi-squared with a subscript of 24. So that subscript is the degrees of freedom. And we'll sometimes see this for a population distribution. Sometimes they might write it in this fashion. So sigma, if you recall, is equal to 2 times the square root it's the square root of 2 times the degrees of freedom. And then we might write a normal distribution with the mean and then the standard deviation. So you might see it in this format sometimes with n and then in parentheses 24, 6.93. So just in case you see that notation there. But usually we'll just use the distribution as chi-squared with a subscript of 24. Third step is let's calculate and do the graph. Now, if you recall, it's slightly skewed to the right for the chi-square distribution. And then what we have here is our alpha is 0.05, and it is a left out because it's lower on the end. And that ends up being that cutoff there is going to be the chi-square, the critical value. And the critical value for this specific example is 13.85, and that comes from a table. I'll show us how to actually figure that out. Unfortunately, the TI 83s and 84s don't have the they don't have a test mode for the single variation. But we could use part of it in the calculator, but we're going to need to get this value from the table, and I'll show that afterwards. And so the chi-squared statistic, we could go ahead and use this formula. And we're going to just plug this in. So n minus 1 is the degrees of freedom times the sample standard deviation squared over the population standard deviation squared, or the variances. And we're going to get about 5.67. So that means that test statistic is to the left. So it's within that critical region. So this area to the left here would be the p-value. And so how do we get the p-value? Well, we could use the tables backwards, but we also have this mode in our calculator, which is the chi-squared CDF. It wants a lower and upper bound and then the degrees of freedom. So we're using that negative E9 for the lower end, 5.67, which is our test statistic, and then our degrees of freedom. So we do have to do that small calculation with that chi-squared test statistic, but then we could use our calculator to go ahead and get the p-value. And we're back to business as usual, where you could just compare the p-value with alpha if you preferred. So our fourth step, let's talk about the discussion and conclusion. P-value is less than alpha, so we reject the null. Then we do not reject the alternative and the claim, because the alternative this time around is also our claim there. So we could use language that we support in this case. So we would say there is sufficient evidence to support the claim that, and we could just copy it word for word, that a single line causes lower variation among wait times. Now, this is not saying that if it's going to be shorter or longer, but the variation, right? So when you go in, it's going to be more consistent, right? As a whole, it might take longer, or as a whole, it might be shorter, but it's going to be more consistent if we have that. And so here's using the tables, and this is directly from the links in the text. So you want to be cautious, though. This is for a lower tail, so we're doing the left side. So I like to always draw a picture of that. So our alpha is to the left here. And if you recall, degrees of freedom were 24. So we're just going to look this up on our table here. So we go down to our degrees of freedom right here, which is 24. and then we go to the alpha, which is 0.05, and then we're just going to go ahead and see where these guys end up meeting there. And that's how we got that 13.85 for that chi-squared, the critical value.